We'll see who pops in. Couple of things that I want to show you first. So Moodle is updated with a bunch of stuff. There are today's PowerPoint slides, obviously. Homework number 5 is posted. So you should be able to see homework number 5 in Moodle. That is up. The due date for that is, open please, Monday, May 4th. So that is the last homework assignment that is going to be due Monday, May 4th. There's also a revised course schedule. So this is the course schedule for the rest of the semester. Look at that, 12 class periods, and we're on Wednesday, so 11 class periods. The topics that we're going to be covering are on here. So we're doing SHA-1 today. Friday's hash functions versus max. Monday is my research, which is going to be fun. The slides will look a little bit different, but that's okay. We're talking about secret sharing schemes, and then we're talking about poker over the phone. So we're going to talk about poker over the phone, which has more of an impact now than it does in class. Friday, Monday, and Wednesday, May 1st, 4th, and 6th are presentations. There were 9 of you who said that you wanted to present live in class via Zoom. So those 9 of you got an email this morning. We will get those presentations scheduled. If you said you wanted to pre-record your presentation and send it to me, that is due Monday, May 4th. So I kind of split the difference on those presentations. There is a spot for you to upload that. So the cryptography presentation slot here on Moodle, if you want to pre-record yours, however you want to do it, you can pre-record it using Zoom. If you want to record it using Zoom, let me know. I can let you use my account. We can log in, make that work. You can share your screen so I can see the PowerPoint or whatever visuals you have, etc. So that's on there. Then revised course schedule one more time. Review the last Friday of the semester, and then remember Wednesday, May, what would that be? 13th at 8 is the final exam. And that I think is going to be cumulative. We'll talk a little bit more about that as it gets closer. Okay, any questions on the revised course schedule, presentations? Again, if you said live, you should have gotten an email from me with scheduling. Please reply to that. I'd like to get those scheduled so you can have a schedule by Friday. So anything else? Daniel, yes.
And is the presentation still worth 10%?
Yes, so the paper is worth 90% of whatever percentage you designated in that category, and then the presentation is worth 10% there, yes. Yes, and remember also, this is the one thing I didn't get done before class today, but that's all right. You're also responsible for watching 5 people's presentations. I'll get a schedule out. I'll get the pre-recorded ones posted on Moodle, so you can decide which ones you want to watch, and I'm going to have a feedback form for you to fill out. So that's your responsibility with the presentations here. Okay, other questions before we jump into class today? Make sure to download homework number 5. Anything else? Other questions? Going once, going twice? All right. Today is going to be a lot of protocol. Today is, I don't want to say hard when we do it in class, but there's a lot of stuff going on here. And so I just need for you to hang with me. Today is me doing a lot of talking. You might want to not take notes live, just listen, jot things down. The PowerPoint slides are presented. They're on Moodle, they're up. So it's probably not the best idea for you to try to write down everything that I say today. Today is definitely a day where you might want to just watch and then go back and annotate your PowerPoint slides, because otherwise a lot of stuff is going to be going on. Okay, so secure hash algorithm. Called SHA-1, a secure hash algorithm. It was designed by the National Security Agency, NSA. It was published by NIST, that's kind of a relation to the NSA, published by NIST in 1993. And the first version was known as SHA-0. That version was withdrawn shortly after publication due to a weakness that was never made public, because this is the government that we're talking about. So the weakness in the original one was never made public. It was revised and republished in 1995, so it took a couple of years, and the new version was known as SHA-1. because again, this is the government and we name things very creatively at this point. The SHA-1 was very similar to SHA-0. There's a single rotation where it differs. So this led to a ton of speculation as to what the actual weakness was, and I still don't think anybody necessarily knows. SHA-1 is no longer secure. I looked on websites this morning. We're up to SHA-3. That is the one that is being used more. That one was released in 2015. So the one that I'm talking about today is no longer secure. It's no longer practically used for government work, but this is the one that is interesting and easy to talk about. John, yes.
Just because I recently read like 13 of these stupid publications or whatever.
Yes.
So SHA-1 is still used in some areas, nothing classified secret or above, and mostly just on systems that were previously built that can't be upgraded.
Oh,
So it
okay,
is
so
deprecated, but it
kind of built
is
into the hardware.
still used a little bit.
Gotcha. Thank you.
Yeah.
But it's not secure, right? So you can get used
For
in
most
limited,
applications.
yeah, limited places. But yeah, so not widespread, not like you said, top secret clearance or anything like that. A little bit. Thank you. Helpful. Other things. Okay, here's where I need you to hang with me because we've got a lot. Basically what I want to do, remember we said last time that hash functions have to have these requirements, right? Arbitrary length input, fixed length output. They have to have ease of computation, pre-image resistance, and then either strongly or weakly collision free. And we said that those are hard to get, right? Those are hard to get, those are hard to do. The reason that we are spending a class period walking through this is because I want to show you one way that you can actually do a hash function. But in order to achieve all of those, there's a ton of stuff going into this. So the balancing act with today is I'm going to talk really heavy on protocol to demonstrate that, yeah, these things exist, but they're sometimes hard to come up with. Okay, so the rationale is I want you to see what a real hash function looks like. I acknowledge that today is an awful lot of protocol and an awful lot of things to keep track of. Just trying to tell you what my reasoning is for wanting to talk this through. Okay, here we go. So SHA-1 uses what's called an iterative procedure. So we break the message up into blocks of fixed size. We can have as many blocks as we want, and that is what allows us to get to the arbitrary length input requirement. So as many blocks as we want is fine. And then we need to pad the last block if necessary so that they all have the same length. Here's what I mean by iterative procedure. The blocks are hashed one at a time, kind of, sort of. So when I say hashed, I mean put through the hash function and a value is output. So we're going to use this thing called a compression function, H prime. And what it's going to do is combine two different inputs, the current block that you're working with, and then the output from the previous round. So that's why I'm saying that blocks are hashed one at a time, kind of, sort of, kind of, sort of. You're using an input from the previous block, and then you're using the current block. It's kind of like it's iterative, right? You do the first one, and then you do the second one based on the feedback that you had from the first one, and then you do the third one based on the feedback you had from the second one, and then you keep going. And so you can see notation for this. The final output when you hash the last block plus the value from the previous one, that's your actual gigantic output of the hash function. So that's what I mean by an iterative procedure. And if we're going to do this for the first block, I need a value from the previous block also, right? But there's no previous block. So I need an initial value x naught, okay? So the x's are the outputs from this compression function, and the m's are the blocks. So this compression function takes as input a block, and then it takes as input the previous value. It outputs a new value, and then you do it again. It takes the next block, it takes this value, it puts them in, it outputs a new value. The last new value is the overall hash for the message. Does that make sense? Okay, we're gonna get deep into the weeds in this, but that makes sense at this point in time? All right, okay. So we need a little bit of notation because this is computer sciencey and there's a bunch of stuff going on here. X and Y is bitwise and mod 2. So it is the minimum of X and Y. If you've got two ones, it's a 1. If you have a 0 in either spot, it's a 0. It's just the minimum of X and Y. I should also say that for you computer science people out there, if I say something that you would not say the same way, that's fine. I'm still right. I'm just not necessarily expressing this the way that a computer scientist would. So you can feel free to wince if you want to, because I'm not expressing it the same way that you would, but this is how a mathematician thinks about it. Okay, an OR, bitwise OR, is the maximum of X and Y. So if you've got two zeros, this is a 0, otherwise it's gonna output a 1. Remember, bits can be 1 or 0. We've got exclusive OR, kind of, sort of. This is bitwise addition mod 2. If you've got two zeros or two ones, it outputs a 0. 1 plus 1 is 2, but 2 mod 2 is 0. So if you got the same value, it outputs a 0. If you have different values, it outputs a 1. That's why this is also called exclusive OR. We've got a not. It changes 0 to 1 and 1 to 0. That one's easy. This one's weird. We've got X plus Y. So this is addition of X and Y mod 2 to the 32nd. Mod 2 to the 32nd. So we are doing addition of X and Y mod 2 to the 32nd. And then we've got this fun rotation. When I first put these slides together, it took me forever to come up with the symbol that would work for the rotation. We've got this fun arrow right here that I finally came up with. So this rotates the blocks of the bits of X to the left by R positions, and the beginning wraps around to the end. Jason, question.
Oh, I missed it. What does bitwise mean?
So I'll make this clearer when we get into hexadecimal notation. You're gonna take a message and you're going to put it into hexadecimal notation. Hexadecimal notation is, so we're used to putting messages into decimal notation. Decimal notation can translate a message into a number 0 through 9, right? And then we're using those and we're good at that. A is 0, 1, B is 0, 2, etc. What SHA-1 does is it takes a message and puts it into hexadecimal notation. So hexadecimal notation uses the numbers 0 through 9, and then it also uses the letters A through E, because hexadecimal is 16. So you've got 0 through 9, that's 10. And then it should be A through F, I'm sorry. A through F is 6 more. So you've got 16 characters going on here, hexadecimal notation. There are many, many ways to take a message with letters and put it into hexadecimal notation. My computer science people, what is the most common way to take a message with letters and put it into hexadecimal notation? What's it called? We know this. Maybe?
Are you talking about just ASCII encoding?
I am talking about ASCII notation, yes. So ASCII notation, ASCII, and I looked it up once and I don't remember what it stands for. So there's a protocol, right? There's a protocol for taking a message and turning it into hexadecimal notation. So you got to hang with me for a couple of slides, and then we can get to how you turn hexadecimal into binary notation also. So binary notation is just with zeros and ones. Hexadecimal notation is with 0 through 9 plus A through F. Binary notation is with zeros and ones. We will talk about how to change that in just a minute. Okay, that's all our notation. We've also got some functions. These are super fun. T, which you don't understand what that means yet, but that's okay. If T is between 0 and 19, I have this function that takes 3 inputs and outputs that. This is why I'm telling you not to take notes live today. By the way, go back and look at the slides, because you're going to be writing really fast and you're going to be missing what I'm talking about, and that's not helpful. So go back and look at the slides as opposed to taking notes live today. If T is between 20 and 39. We've got this function here. Takes as input 3 things, output something. So that one's a little bit less messy with exclusive ORs. If T is between 40 and 59, we've got this function going on here. There's an extra space in there that doesn't mean anything. It's the same idea, I just got some extra spaces in there. If T is between 60 and 79, then we're back to the same function that we had for between 20 and 39. So those two functions are the same. By the way, there is no expectation whatsoever that you have any of this memorized. That is completely ridiculous. But there is a problem on the homework where you have a choice. You can either execute SHA-1 for one block, or you can write a program that executes SHA-1, either way. So you might have to work through this. Okay, so we've got these functions. I understand you don't know what T is and you don't know what these functions are doing. That's okay. We are building steps here. Next, we've got some constants that get used in SHA-1. Again, we've got these values of T. If T is between 0 and 19, there's my constant. Remember, this is hexadecimal notation. That's why there's an A in there. So I can have letters 0 or numbers 0 through 9, and I can have letters A through F. That's my constant. That looks totally and completely random. It's actually not. And there is a question on the homework assignment, once again, that you can choose to do if you want, that tells you where that constant comes from. It isn't as random as you think it is, which is kind of cool. If T is between 20 and 39, we've got this next constant going on here. Once again, not as random as you think. Promise. That one looks a little less random. There's a little more structure there. T between 40 and 59, that one looks more random. And then T between 60 and 79, that one also looks more random. There's some structure here. I'm not going to tell you what it is. You can do it on the homework if you want to, but there's some structure going on here with these. Okay, so these use hexadecimal notation. I am going to, give me one